Hi everyone, welcome back to this third video in a series to support the self-study assignment analysis of N of 1 trials. In this video we're gonna be diving a little bit more into the distributions and variables and how we can use these for the core concept of Bayesian statistics, which is Bayesian updating. So there are two key concepts underpinning this, and the key concept number one is that parameters or unobserved variables can be used to generate data, and vice versa, data can be used to infer parameter values. And key concept number two is likelihoods are similar to priors and they are both expressed as distributions. So here we have an example of a distribution or a likelihood where there's only two options. So this may be something like a coin toss or a yes no, alive or dead, or in this case we have a model of the Earth and we want to determine the proportion of Earth that is covered by water. So let's say we have a ball which has a map of the Earth on it, and as a means of sampling it, we will toss up the ball, toss it in the air, and if we catch it, the place where our right index finger is pointing at. So if it's on water, we return a water observation. If it's on a landmass, we return a land observation. And let's say we've done this 9 times, so we toss the ball in the air 9 times, and this is the sequence that we've got. So the first time is water, second time land, water, 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 land, water, land, water. So this means that there's 6 times water, 3 times land. So what is the what if we assume that the probability of water is in fact 15%? How likely is this this observation that we got 6 out of 9 times water? Then we can get simply from this distribution the binomial distribution, which is yes no, and we can say, okay, this is our observation, our success, 6 times water out of 9 tosses, and with a prior probability of 50%. Then we're saying, okay, so the posterior probability that that 50% of the Earth is covered in water is actually 16%. And this is basically all there is to Bayesian analysis. So let's say, okay, so 50% is a bit of a gamble, and we would like to get a more in-depth view. What could we do? Well, actually, what we could do is, instead of just trying 50%, is that we could try a whole range of possible values. How can we do that? So what we can do is that we define something that's called a search grid, where we don't only take the probability of 50%, but we can take a whole series of values. So that's what we've done here. We define the probability grid. It's what this vector is called, P grid, and it ranges from 0 to 1 in 21 steps. And if we look at what's inside this vector, then we see that it's a range of numbers. So the lowest number is 0, the highest number is 1, and it goes up in steps of 0.5, 0.05, and in the middle is 50%. And we can try all these numbers and see what happens. We also define our prior, which is in this case a non-informative prior. How can we say it's non-informative? Well, we've just repeated the number 1 21 times, saying that each of these values, so 0, 0.05, 0.50, and 1, they're all equally likely. They've all been assigned the same amount of weight. This is something that we call a non-informative prior. Okay, so we combine this this search grid where we try each of these values with the data that we've seen, so 6 times water out of 9 tosses, with the binomial distribution to create a likelihood. And again, this is just a vector, so we just see what's inside this, and we get a whole bunch of numbers. We multiply this by the prior to get a unstandardized posterior, and now if we take the sum of this unstandardized posterior, it sums to a little over 2, which is kind of hard to interpret. So what does 1.12 to the minus 6 out of 2 mean? I don't really know. So we take the unstandardized posterior and divide it by the total the sum, so the total value of the posteriors, and this way the sum of the posterior will be 1. So it ranges, the posterior ranges between 0 and a maximum of 1. And actually what this means is that we have returned probabilities, and you've already seen it here on the right hand side. This is the probability plot. Let's zoom in a little bit, of the posterior probability of water by the prior probabilities of water. So we said beforehand that we believe that the likelihood of the Earth being being no water on Earth was equally likely as the Earth being completely covered in water. So basically 0% or 100% water. But having seen the data and having seen at least one observation of land, then we know, or of water, then we know that 0% water is out of the question. We've also seen at least one observation of land, so 100% water is out of the question. And having seen that 6 out of 9 tosses returned water, then the highest density, or the most observations, will be 0.67 or 76%. 67% water. So 6 out of 9. That makes sense, right? And that's really all there is to it. All there is to Bayesian analysis. So what you do is you think about what would be a distribution or a likelihood function that fits the outcome, where we have 2 options here, water and land. So the binomial distribution is what you would use. Then you define a prior probability, or a range of possible prior probabilities over which you're going to search. You define a prior, which in this case was non-informative, and you add the data, the observations that you had, so 6 successes out of 9 tosses. You do the multiplication, you standardize by all the possible values, and you get a result. That's all there is to it. So feel free to play around with this. Next time we will go a little bit more in what you can do with these kinds of posteriors and how you can use them to answer scientific questions. So thank you for your attention, and see you in the next video.